So informally, what does the FTC mean? What does all that mean, part one and part two? Well, here's part one. And the informal reasoning is actually closer to what Newton and Leibniz were doing when they were proving this. This is closer to their line of thought. So first off, let's just consider a nice continuous positive function. Let's not mess around with any negatives. Of the area underneath the curve f of t from a until x. Right? Now we know from the definition of what the definite integral is that this space we'll call a of x. A of x is the area underneath the curve from a until x, which equals that integral right there. Now the question is, what if you move over a very small amount to x plus delta x? Right, now this space right here, this extra space that you accumulate when you move from x to x plus delta x, we'll call that delta A. This is the change in A when you move from x to x plus delta x. And we can approximate it with this rectangle right here, where we use f of x as the height and the base is delta x. So it's approximately f of x times delta x, which you can rewrite that, if you were so inclined, as f of x is approximately delta A over delta x. Now, as delta x approaches 0, this becomes exact, because as delta x approaches 0, it stops being an approximation and becomes the exact value, which means as delta x approaches 0, you get equality. And what is this? That's the change in A over the change in X. That's just A prime. This is A prime. So the slope of the area function is f of x. And there's actually a better way to explain that I wish I had done instead. But let's just explain this in a slightly different way. So A prime equals f of x. This is dA dx. And this is the y value, right? So those two are equivalent expressions. I just chose to write it down differently. And if we went to differential form, we get this right here. Oops, there we go. This says that the change in the area is just the y value, right? If you move over a tiny amount, dx, the change in area is just the y value times how long you were changing for. So this gives you the change in the area. It's just the y value, which is the height, times the base, which is this infinitely small value dx. And that's the change in area. And if you kind of work your way backwards, that means that dA dx is y. How fast is the area function changing? It's changing y fast. It's kind of like if you decided to draw the area one line at a time. It's like there's one y value at a time. The y value is how fast the area is changing. I could probably stop doing this, but I'm so close to the end. Done. So that's about as well as I can explain that. That the tiny change in area is the y value times the tiny change in x. And then if you rewrite that, how fast the area is changing is the y value. Part 2, which again for us is kind of the more important part in terms of its impact. Part 2 is really just an example of distance equals rate times time. How far you go is how fast you go times how long you go for. And the same is true for functions. So the change in some function f, I'll use big F, is how fast f changes, the rate of change of f, times the length of the interval that f is changing on. Right, so for example, let's say you had some function f such that how fast it was changing, which is its derivative, was just like 3. Right, so the slope is always 3. That means y goes up 3 when x goes over 1. And let's say that the length of the interval delta x is like 6. Let's say that you're going from like 2 to 8. Well, how much did your function change by? If it's going up 3 for every x value over, and it was doing that for 6 x values, the change in f is just 3 times 8. Or sorry, 3 times 6. Right? The net change of f, how much your function changed, is just how fast it was changing times how long it was changing for. But what if your function is not constant for its rate of change? What if your function had a variable rate of change? Well, if your function has a variable rate of change, what you could do is break the interval into a bunch of tiny pieces. You break the interval into a bunch of tiny pieces. You take the average slope on each of those tiny intervals, multiply the slope times the length of the interval to get how much the function changed on that one piece, and then you add them all up. So if we do that again, if we kind of write that down with sums, the net change of f will be approximately the sum from 1 to n of this right here. Big F prime times delta x is how fast the function was changing times the length of the interval. Right? And since we broke our interval up into a bunch of tiny subintervals, when you add up all those changes, it gives you an approximate of the total net change. And we have equality if n is infinity. So the limit as n goes to infinity of the sum from 1 to n of how fast your function changes times how long it's changing for. So again, just to recap this, because this is complicated, the change in your function is how fast the function changes times how long it's changing for. Right, so that's just true. If your rate of change is constant, then it's easy. It's just how fast your function's changing times the interval length that's changing on, and you get your change in f. But what if big F prime was not constant? You can't just do big F prime times the length of the interval. Instead, you break the interval up to a bunch of tiny pieces, each of which has length delta x. You find how fast the function's changing on each subinterval, multiply those two, and that is your distance equals rate times time. That is your approximation for how much the function changed in that interval. When you add up all those intervals, it gives you an approximation. And if there are infinite intervals, it gives you the exact net change. Now, we should write these two differently. Net change of f, well, that's the function value at the end point minus the function value at the start point. That's how much the function changed, where it started minus where it ended minus where it started. And this limit is a definite integral. It's a Riemann sum. And there you go. If you want to find the integral of some function, just find its antiderivative and do the difference. So really, it's like you're doing rate times time on a bunch of tiny time intervals. You take their sum and it tells you how much the function changed. That's how I like to interpret part two. Part two is really just a kind of the next level of this simple formula. The distance, which is the net change, is just the sum of all those rate times times. Just a bunch of how fast the function's changing times how long it's changing for.